Welcome everyone and thank you for watching this presentation. Let me start by giving you an overview of the structure of this presentation. Our journey today will begin with the first introduction where I set the stage for the research problem and its significance. Next, we'll dive into the key contributions of this work, highlighting what sets it apart. Afterward, I'll provide some background to help contextualize the study, followed by a discussion on related work to know what others have already done in the field of smart contract vulnerability detection and to show how this research fits into the broader landscape. Then we'll move on to the method, detailing the experimental approach and framework design. From there, we will examine the results and analysis where I'll share the findings and their implications. Finally, we'll wrap up with the conclusion and future work, summarizing the study and outlining potential next steps. This roadmap will ensure a clear and structured presentation of the research. So let's dive in. Let me begin by explaining what a smart contract is. I mean, smart contracts are essentially self-executing contracts with the terms of the agreement written directly into code. These contracts run, of course, on the blockchain technology, enabling them to automatically execute predefined actions such as transferring assets once a specific condition are met. The benefits of smart contracts are significant. They enhance transparency, improve efficiency, and of course provide a higher level of security. They also minimize human error and reduce the need for trust between parties. Qualities that actually make them revolutionary for the industries like finance, supply chain, and many more. However, smart contracts, like any other softwares, also face serious challenges, primarily around security. They can be vulnerable to exploitations, as we've seen in some high profile incidents. For example, the 2016 DAO attack led to the loss of 3.6 million ethers, and in 2018, the BEC token incident exploited an integer overflow, resulting in the creation of 6 billion tokens. These examples underscore the critical need for robust security measures, which is what my research seeks to address. Building on the previous slide, let's discuss some key concerns surrounding smart contracts and the gaps in existing solutions. Smart contracts are immutable and often manage sensitive data, which make detecting vulnerabilities absolutely critical. However, manual methods of analyzing and auditing smart contracts are becoming increasingly inefficient as the complexity of smart contracts continue to grow. So, to address this, researchers have deployed and built several tools to detect common vulnerabilities. For instance, Slater is a static analysis tool capable of identifying issues like reentrancy and variable shadowing. Mad Max focusing on out of gas vulnerabilities, while SFAS use dynamic analysis to detect timestamp or block number dependency and even integer overflow vulnerabilities. Despite these advancements, there are still research gaps. Vulnerabilities such as signature malleability, hash collisions, and code with no effects remain largely unexplored in existing datasets and tools. My research aimed to address these overlooked issues, contributing to a more comprehensive approach to smart contract security. In this slide, we present the key contributions of our research to the field of smart contract security. First, we investigated the root cause of three vulnerabilities that have been largely overlooked in existing studies, which are signature malleability, hash collisions, and code with no effects. By thoroughly analyzing these vulnerabilities, we aimed to understand their underlying mechanisms and implications. To support our research, we built a dedicated dataset of smart contracts specifically designed to exhibit these vulnerabilities. This dataset not only served as a foundation for our experimentals, but also offer a valuable resource for the wider research community. Finally, we introduced SmartSentry, a modular smart contract vulnerability scanner. This tool, or this framework actually, is capable of detecting the three vulnerabilities we focused on, and its modular architecture allow for easy integration of future enhancements. Through these contributions, we aim to address critical gaps and advance the field of smart contract security. In this slide, we will briefly explain the three vulnerabilities that we focus on in our research, highlighting their meaning and potential impact, but without going into the root cause of each of the vulnerabilities, because we will see this in the next slides. The first vulnerability is the signature malleability, which refers to a vulnerability where the digital signature of a piece of input can be altered without changing the actual signature. Without making the signature invalid. The second one is hash collisions with the multiple variables of varying length, which occurs when two different inputs produce the same hash value. In smart contracts, this can result in unintended outcomes such as incorrect contract execution or fraudulent behavior, as the contract may not distinguish between these two different inputs that should be handled separately. Lastly, code with no effect is when a piece of code in a smart contract has no actual impact on its execution. This may lead to waste of gas costs, inefficiency, or even security risks if the unusual code is exploited in the future. All of these vulnerabilities pose significant risks to the integrity and functionality of smart contracts, and understanding their implication is critical for deploying robust security solutions. In this slide, we will discuss existing techniques for vulnerability detections, focusing on both dynamic and static methods. First, let's look at dynamic vulnerability detection. Dynamic analysis can be divided into main categories: black box and gray box analysis. In the black box analysis, the system is analyzing without a knowledge of the underlying source code or architecture. The goal is to identify vulnerabilities by subjecting the program to various inputs and observing if it crashes or behave unexpectedly. In contrast, gray box analysis combine dynamic testing with some knowledge of the program structure, either manually or automatically, to enhance the analysis process and reduce time. Tools like AGIS, developed by Christoph and all, use dynamic control flow analysis to track the execution of instructions and dynamic change analysis to trace data flow. Similarly, SFuzz, developed by Nguyen et al., utilizes feedback-guided adaptive fuzzing, while Reward by Liu et al. Automated the detection of reentrancy vulnerability through fuzzing-based analysis. Despite their strength, dynamic analysis has limitations. It may not explore all possible program paths and inputs, which means some vulnerabilities could remain undetected. It can also generate false positive or false negatives, potentially leading to either missed vulnerabilities or unnecessary alerts. Furthermore, the dynamic analysis can be computationally expensive, particularly when assessing large, complex smart contracts. Now, let's move on to static vulnerability detection. Unlike dynamic analysis, static analysis involves evaluating the source code or binary code of a program without executing it. This approach allow for a thorough examination of the program design, logic, and structure, helping to uncover vulnerabilities before they can cause harm. Static analysis like analysis tools like Slither, SmartCheck, or even Oint play a pivotal role in detecting smart contract vulnerabilities. Slither, for example, analyzes Ethereum contract by first converting the code into an abstract syntax tree and then applying various analysis using Slither ER and internal representation language. SmartCheck, on the other hand, utilizes both lexical and syntactical analysis, generating an XML parse tree to identify vulnerabilities through XPath queries. Oyent applies symbolic execution to identify vulnerabilities based on symbolic representations of input variables. While static analysis offers comprehensive coverage, it can sometimes struggle with the complex contract behaviors, especially when evaluating large code base or handling specific edge cases. Now, let's talk about the root cause of the vulnerabilities. The first vulnerability we have talked about is signature malleability. The root cause lies in the failure to enforce constraints on the S component of the DSA signatures, allowing multiple valid signatures for the same transaction due to non-unique signature definitions. The second vulnerability is the hash collision with multiple variables. This vulnerability arises from the lack of padding in the ABI.encode packet function, leading to identical hash outputs for different input combinations during concatenation. The last one is code with no effect. The vulnerability is caused by code structures that lack functional impact, such as conditions that always evaluate to true or false, missing critical parameters, or improperly placed operation outside control blocks. Now, let's see our framework design. The SmartSentry framework consists of three components: the pre-compiler, the compiler, and the analyzer, forming a comprehensive smart contract analysis pipeline. The first component, which is the pre-compiler, retrieves the input codebase, including dependencies and anything related to preparing for a compilation process, ensuring a cohesive environment for the subsequent stages. The compiler process the code to generate critical artifacts like the abstract syntax tree and control flow graph, which provide structural and control flow insights. The last component, which is the analyzer, which is the core of SmartSentry, uses static analysis technique to detect vulnerabilities, focusing on modularity to isolate and enhance individual detectors. This modular design facilitates the seamless addition of new detectors, ensuring adaptability and continual advancement in smart contract security. In this slide, we will outline the experimental design used to evaluate the effectiveness of our approach. Our approach is composed of actually three phases. The first one is the dataset preparation, as we didn't find any dataset that has the three vulnerabilities we already discussed. We needed to build one for this and to actually find another 1000 contracts to see if our tool will be capable of detecting any of those vulnerabilities in real world production smart contracts. The second phase is the controlled testing. In this phase, we try to run our framework on vulnerability on smart contract. We know it in advance that they have those vulnerabilities to see if our framework will be capable of detecting those vulnerabilities. Then, and in the last phase of this experimentation, we try to see how well our framework will be able to work on real world smart contracts, and at this stage we run our framework on 1000 real world production vulnerabilities. In this slide, we focus on the dataset used in our research. We identified a gap, as we have already said in the first slides, in existing dataset, which lacked coverage for vulnerabilities like signature malleability, code with no effects, and hash collisions. To address this, we created 9 custom vulnerabilities smart contracts targeting these specific vulnerabilities, serving as a benchmark for future research. Additionally, we compiled a real-world dataset of 1,000 recently validated smart contracts from Etherscan as of January 18 to 2024 for performance evaluation. This dataset allowed us to test our tools' scalability and effectiveness on contracts deployed on the Ethereum blockchain. Now, let's see the results of our framework. In the first phase of our experimentation, the results were promising, as SmartSentry successfully compiled the 9 contracts and accurately detect every injected vulnerabilities. This confirmed the tool effectiveness in a controlled environment. The second phase, where we were trying to focus on performance, Testing SmartSentry on 1000 real-world smart contracts from Etherscan, the framework compiled 98.8% of contracts within 29 minutes and 42 seconds, detecting 7 vulnerabilities which were manually verified by a security auditor. However, code with no effect vulnerabilities were not identified in this phase, likely because these issues are rare in live ecosystems. These results validate Smart Sentry potential in a real-world scenario and highlight its ability to enhance blockchain security. In conclusion, detecting vulnerabilities is crucial for securing blockchain-based application, and our work contributes significantly in this field. We have dissected the root cause of three previously underexplored smart contract vulnerabilities, which are signature malleability, hash collision, and code with no effect. We also built a comprehensive dataset of vulnerable smart contracts and introduced Smart Sentry, a modular vulnerability scanner that effectively detects these vulnerabilities. Looking ahead, there are exciting opportunities for future work. We aim to expand vulnerability detection to cover more attack vector and integrating automation using machine learning to enhance the framework capabilities, allowing for fast and more accurate detection of emerging threats in smart contract security.